So we're going to do this AC generators thing. And AC, what does AC mean? Talk about an AC generator. What are we talking about? Alternating current. So we're talking about a generator that generates electricity that goes one way and then the other way. One way, then the other way. And what we're going to see is that frequency at which the current alternates its direction is going to be the same as the frequency that we turn our generator around it. And so think about a generator. If we simplify it down to the most basic components, what we've got is a magnetic field, a north and a south, and that's often produced by an electromagnet. So often to make an AC generator, you'll have a little electric current that you need to put into it to produce a really strong magnetic field. It doesn't have to be, but the magnetic fields we can get from electromagnets are much stronger than the ones we get from fixed magnets, just for size. And so this magnetic field, this north-south, is often going to be produced by an electromagnet. And then inside that magnetic field we have a loop of wire which we then rotate around. And so there's a couple of quantities we're going to think about. Starting from that vertical position where the flux, the magnetic flux through that coil is maximum, the angle that our coil of wire has rotated, theta, is just equal to omega t, where omega is the rate of rotation and t is the amount of time it's been rotating for, assuming that our generator is rotated at a constant angular velocity. And then coming across to area here and thinking about what an equation for area might look like, given that the area is constantly changing. The area of the coil is just the length times the height, and as we twist that coil, that area is going to be length times height times the cos of the angle. The cos of the angle is at time 0 it's maximum, and then as we rotate it, it's going to go initially down towards 0 at the instant when that coil is parallel to the field. And so theta is just the same as omega t, and so we've written an equation for area as a function of time. So area is LH cos omega t, and we can see that that's LH is just our area of the coil, and so area as a function of time is just area of the coil cos omega t. And then finally we know what we're interested in for an induced voltage. We have to think about magnetic flux, and so flux is B cross A, and so we can put our equation for magnetic flux into there and say that phi is BA cos omega t. So we've got all of the components we need here to build an equation for the voltage that's induced across this. Okay, so induced voltage, we're thinking about Faraday's law, and so induced voltage is minus d phi by dt. And so what we're going to do is we're going to differentiate our phi as BA cos omega t with respect to t. And so what do we get? What do we get when we differentiate BA cos omega t? So the induced voltage is minus, but minus, plus. So the induced voltage is BA omega sin omega t, the induced voltage across the inductor. The thing that we can add to this is usually when we're building an inductor, when we're building a generator, we don't just put a single loop of wire inside a magnetic field. We're going to put like many loops of wire, knowing that each individual loop will have the voltage and the same voltage induced across it, and so those voltages will add together. So if we adjust our equation for n loops of wire, the induced voltage on that generator at any time is going to be BAN omega sin omega t. And so what we're seeing, if we have a go, we're going to have a go in a moment in graphing this voltage up, is that it's a sine curve and the amplitude of that sine wave is just equal to BAN omega. So the maximum voltage produced by our generator depends on the magnetic field strength. The stronger the magnetic field strength, the bigger the voltage. The area of the coil, bigger area, bigger voltage. The number of loops of wire, more loops, more voltage, and how fast we turn the handle on it. The omega, the greater the angular frequency, the greater the induced voltage. So what does the output voltage from this thing look like when we turn the handle on it? Well, it follows a sine curve. So thinking about our picture, initially we had the coil so that it was at right angles to the magnetic field, and that meant that the flux through our coil initially was maximum. And as we twisted that coil, the angle of the coil to the magnetic field adjusted slightly, but because as you turn that, the actual flux through it only changes fractionally, we get zero induced voltage at that point when the coil is vertical. But then as we turn the coil through the first 90 degrees until the coil is now horizontal, at that point when the coil is turned around to be horizontal, it's got zero flux, zero magnetic flux through it, but just a moment before it had some. And to go from some to zero, that's a really big change. And then to go from zero back to negative some, that's also a really big change. So we get a really big induced voltage at the point where the coil is parallel to the field. At the point where the flux is zero, that's actually where we get our greatest rate of change of flux, and so the greatest induced voltage. And then the coil rotates round to 180 degrees, back to maximum flux through it, and zero induced voltage. Then another quarter of a turn on, we're over here, and once again, we're getting that maximum rate of change of flux at the same time as we've actually got zero flux through the coil. So if we think about how much magnetic flux through the coil, zero, rate of change of magnetic flux, maximum, so induced voltage, maximum. The reason that this is a negative and that this is a positive is just that the loop is the other way up, and so that means that the current is now flowing the opposite way through the coil. If we have the top bit of coil was moved to the bottom, that means that here the current was flowing one way, down here the current's going to be flowing the opposite way, and so lo and behold, we've got that alternating current. First we pushed the current one way, now we've grabbed hold of it and we're pulling it back exactly the same amount the other way, only to push it forward again. And so what these AC generators do is they're kind of shaking the electrons on the wire, pushing them backwards and forwards, making them follow a simple harmonic motion kind of path. We can see that the driving voltage follows the same sort of curve that we see from simple harmonic motion. So we're going to apply our simple harmonic motion concepts to help us understand how AC circuits respond to different frequencies and different sizes of voltage.